My name is Hughes-Croucher. I work for a company called Joyent, which you've maybe heard of. We do stuff with Node, which you've also maybe heard of. And yeah, I'm writing this book. I don't recommend writing a book. It's a stupid idea. If anybody ever tells you to write a book, you know, just ignore them or hurt them or both. But this is the book that I'm writing. In case you're wondering, that's a common tree shrew, because O'Reilly clearly let me pick my animal. You know, so the talk is multi-tiered node architectures, but you know, I wanted to kind of recap some stuff. I think the people at JSConf are always really smart, but I think often kind of looking at the core principles of what we're trying to achieve really helps. So you know, one of the things that we want to do when we write servers is minimize the client response time, and this is actually like a big draw of why people use Node, right? Is we want really fast servers, because you know, sometimes people just can't wait to do stuff, and you know, that can be an issue. In case you're wondering, I also used to work for Yahoo, so that's a Yahoo bathroom. So goal number 2 is, well, sure, we want really fast response times, but you know, heck, I only have so many servers. You know, I mean, I guess we could buy like a server for every user that we have, and then all of their response times would be really fast. But obviously nobody can afford to do that. That's stupid. So it's, you know, we have these two conflicting goals. It's like, how do we balance these things? Because obviously, you know, at some point we hit the capacity of our servers, and sometimes, you know, even if you're planning capacity, there are issues there. So I like to think of this in kind of the critical path. Like, one of the things I think people think of like these really generalized models of computing, and what it comes down to for me is we have a critical path. This is what an internet application looks like. A modern internet application looks like this. You have this big red blob of like network latency at the front, and this is really simplified, but you know, the talking back and forth with a web client over the internet is really slow compared to the actual amount of computation it takes to render a web page. Talking to the database is really slow compared to the actual time it takes to do a query. In general, not all queries, but in general, this is generally true. I mean, think about Google. If every time you typed in a search query, Google went out and spidered the entire internet, compiled you know, a search index, and then gave you back your result, it would be like a month. The point is that we take all the computation as far away from the user as possible, so when the user is actually interacting with the website, the web application, whatever system it is that we're doing, the maximum, the biggest pieces of this time is some kind of routing, some kind of network transfer, and the actual amount of computation is as small as possible. And these are the models of applications we build now. So the traditional way that we do this is we pre-allocate resources to the client for the entire duration of the request. We go, here you go, here's a bunch of resources. And that gives you efficiency within each individual connection. You give a bunch of resources away, and you get a lot of efficiency. It's like, here's a big slice of resources, and that means that the response time for this individual connection is going to be really fast because I've already given them all the resources that they need to do this. So as soon as anything happens, I'm instantly ready to go. So that kind of makes sense. You know, I think of it like this. You know, if the Pi is my server, I have like a certain amount of resources that's just dedicated to running, you know, whether it's Node or Apache or, you know, Tomcat or whatever. And then every request, you start to share out the Pi, and you give each one of these to a request. And you know, that's great, but we basically heavily waste memory in order to serve the fastest, most optimal request. And when you run out of, you know, memory, the server gets overwhelmed, and that's, you know, that's kind of bad. It's like fighting off lobsters with a stick, I guess, to stretch a metaphor. I don't know. Actually, I tried this talk somewhere else, and somebody heckled me and said, "Those aren't lobsters, those are crabs." You know, it's kind of weird. I mean, to be honest, I don't know this gentleman well enough to know if those are crabs or not. That was awful, wasn't it? But seriously, I mean, I think it's a model that kind of, it makes sense in principle, but we have these real world constraints. We can't have as many servers as we want. And this is where the event loop comes in. So if you don't pre-allocate memory, what happens? we create a placeholder for slow tasks. So this is kind of, I mean, this is still kind of Node 101 stuff, but we have all these placeholders, and then we have this shared work resource. Like now I have some work to do, I'm going to do it, the server's going to use memory in order to deal with this one specific task. We have the first in, first out model, so we have a bunch of events. You can see that for each individual event, whether it's like an event created by the Node application or from the OS, it goes in and it comes up. But you know, that makes the server more efficient, but it then creates this thing where we can't block the event loop. So people start to, you know, wonder, well, I'm using this model, how do I actually make the most of my servers? What are the architectures that really help me? So if I do big work in the event loop, then we can only serve after that request is finished. So, you know, this is like a different programming model. People are like, well, I get the other thing. You know, I just have like one thread per user, and I don't have to think about it. But now I'm in this shared memory. You know, I'm sharing all of this stuff. How do I do that? I have to worry about these big tasks. So blocking the event loop is just bad. Nobody wants to do that. You know, don't worry. I'm going to run out of bad metaphors soon. But nobody wants to block the event loop. So it's like, how do I do that? How do I create an architecture with Node that makes it work efficiently? So this is the obvious architecture, and everybody uses this. You know, it's not rocket science, but it is a tiered architecture. I have my client, and then I have some kind of like Node front end, and then I have a database. And this is, I mean, this is like a really simple architecture, but it's clearly multi-tiered. The database is doing stuff that isn't in the main Node process. We're not blocking. We're using asynchronous I/O. And this already is a multi-tiered architecture. You're pushing the database work out so it's not blocking the rest of the Node process, right? I mean, we could just, you know, we could have all of that together. What about something like this? This is something that I think a lot of people were starting to play with. Well, you know, if big things in Node are bad, how about I do something like this? So I want to do clients. Maybe I want to use JSDOM in order to render all of my results. People really like the idea of doing stuff with JSDOM, and that's cool. I think that's really interesting. But it's like, well, what if, you know, if all of the JSDOM stuff is really big, I should move that to like a separate thing outside of my main Node process, right? And then you end up with an architecture like this. Well, why would you do that? One of the things people want, well, parallelization. Like I'm spreading out my load. I'm creating more task synchronization. But if we look back at this diagram, when you're using something like JSDOM and you're just increasing the size of these computational units, you're just increasing the size, the critical path is still the same. The path between the user asking for a request and getting one back is the same. You've just added more computation. So maybe the actual balance on the critical path is different. Maybe now computation is 30% of the critical path instead of 10 because you're doing more work on the server, because you're using more JavaScript. I think that's okay. And this is the thing, is people think that, that doing that helps them. If you use non-blocking I/O, you're removing all of the resource allocation during latency. So all of those latent periods you can forget about, and the computation is still the same. So pushing all of that client-facing processing off the main process, so if we look at that architecture again, you know, pushing that back to another thing that's in the same critical path isn't helping you. In fact, it's actually just making it worse. You're pushing that processing, so you have to have another jump. You have to have more HTTP requests. It turns out that it's okay if you have a bunch of like Node front ends all running Express, and your individual response time is now 15 milliseconds instead of 1 millisecond. Well, that's okay because you're doing more work. Just get more servers. You're going to need more servers anyway. So I think this is something that people conceptually understand this idea of I don't want to block the event loop. But if you just are doing more work, then that's okay. So let's look at some other stuff. What other kind of architectures might we look at? And I think this is where it starts to get more interesting. So I've got a client. I've got a front-end farm which is talking to the database. Maybe this is Express. Now, the logging this is something that isn't on that critical path. This isn't involved in getting the response to the user as fast as possible. Instead, now we've got something where it's, this is something that's out of band. This is something that, and if you, is Matt Rainey around somewhere? Hey, Matt, there he is. He's really tall, but he's sitting down, so now he's just putting his hand up like an average height person. Matt is doing a bunch of stuff in this kind of model. So I recommend talking to Matt if you want to talk to somebody that's running at scale a bunch of stuff where he's pushing the work which isn't user-facing out of band. And this is where it's useful. If you have this process that you want to work as fast as possible, and you're sharing memory, things like logging, just throw it at Redis, throw it at some node process that's going to take it to Redis or Riok or Couch, and get it out of the way of the user. If you have, and this is, I mean, a really good example of this actually is standard error. If you try and write to process.standard error on your main node process, that actually blocks. If the kernel write buffer is full, that will block your whole main node process. So the better thing to do is if you want to log to standard error, which you don't really need to, but if you really did, throw it out to a separate node process that's going to write to the that file descriptor on your behalf. You know, you can share the file descriptor, you can pass it over, and it will write to it on your behalf, but you've got to get the things that are blocking that aren't to do with actually serving the request to the user out of the main band. And this is where it makes sense to start splitting stuff up. So move work which isn't user-facing out of the event loop. Don't worry about the stuff that is. That can stay there. That's fine. It's just regular work. And then, of course, you know, I mean, I've started displaying some of these things now as stacks. Use pre-forking. So just, you know, create things into farms. You want to use all of your, you know, all of your cores on your machine. Do people know about cluster? Hands up people that are using cluster. A few people. You can do this by hand. I strongly recommend cluster. I've heard like TJ and Guillermo are good at writing node apps. Apparently that's true. So this is how you use cluster. So I create a file called children.js. I create a server. In this case, obviously, it's really simple. In your case, it's going to be a lot more complicated. Create the server. You have a function which does stuff. And then all I'm doing is instead of actually listening myself, I just export the server. Do people use Spark too? Anybody using Spark? No? OK. It's like that, if you've seen that. And then to run it, instead of just running it as normal, I just have a wrapper script. So the wrapper script includes cluster, cluster.children, so I'm giving it the name of my JavaScript application, and then I tell it to listen on port 80. Now what's going to happen is in this scenario, instead of just starting a single node process, which is what typically happens when you just type node my script, it's going to start 20. And what it's going to do is it's going to create a main process, which is going to create file descriptors. It's going to listen on port 80, and then it's going to pass the file descriptors. It's going to pass the socket, that one socket on port 80, to all of the other child processes. But it's going to, the way that Node does that is going to pass them at a kernel level. So basically, we're going to tell the kernel, I have these 20 processes, and I want you to give anything that happens on port 80 to one of them. And one of them is going to pick it up. So now, you know, if you have a server with, you know, 24 logical cores or whatever, so say it's, you know, say it's just like a regular 8 CPU machine, and each of them has, you know, four cores. You know, you can use a bunch of those cores in order to do your node work. That's great. That you now have a lot more capacity within your node, and this is by far the easiest way to do it. You can obviously, I mean, like go and read the code. It's, you know, I think it's like 1,000 lines or less. You know, so you can go and see what they're doing. But Cluster has a bunch of really nice tools for management and, you know, keeping the nodes hot and restarting them and stuff. And then obviously that's great, but you can also use load balancers to distribute. This is all like regular stuff. Node proxy. I don't know if you saw Charlie's talk. You know, those guys wrote Node proxy, Squid, Varnish, Har proxy. You know, there's a bunch of stuff. I'm not going to really talk about that. And then the final thing I wanted to talk about a little bit. Let me just check my time. Right, so we've got 5 minutes. So sharding. Sharding is kind of hard. I mean, you know, there are definitely strategies for sharding. I think one of the earliest kind of good references that I like on sharding is Cal Henningson's book on Flickr. I think it's like Scaling or something like that it's called. It's an O'Reilly book with a fish on it. And you know, node processors can handle lots of clients. So you can do really big shards. This is actually one of the things that's really nice about Node is like typically when you're doing sharding strategies, it's like, well, you know, if each of my machines only gets like a couple thousand clients, you know, the logical like separation, say you've got like a chat room. If we were building a chat room and you want to distribute across a bunch of things, and you have 30 people in a chat room, well, it gets difficult, or like hundreds of people. Because Node will happily handle hundreds of people in a chat room, you could just have like one process per chat room. That's a really common approach that people take. There's all kinds of things, but because Node processes can handle lots of clients, you can do really big shards, and that's kind of nice. The other thing that's kind of nice is that's a single process. When you start actually doing like multi-core Node on a single machine, is you can use Unix sockets. So you can use those same file descriptors to start passing a lot faster communication. So file descriptor sharing is actually really nice because you can start to have the same processes listening to the same file descriptor. So you can basically create a bunch of file descriptors, pass them to a bunch of child processes on the same machine, and say, you guys now have a really efficient way to do multicast on a single machine. And the kernel is facilitating all that, so you're getting a really fast inter-process communication. Now, I'm not saying that's easy. I'm not saying that you don't have to think about your architecture, but one of the things that's great is because Node is scaling so much on a single machine, is you can start to glue 8,000, 12,000, whatever it is, 30,000 people to a single machine and say, you guys are a shard. And that, depending, I guess there's a few guys probably from Facebook or some like other really big companies, but for most applications, something even that simple means that if you can just glue, however many people it is to one machine, you've just achieved the amount of scale that you wanted. So that looks something like this. Client load balancers glue people to a machine, and then the machine then shards out a bunch of processes which can share some file descriptors or Unix sockets in order to do that really, that much faster than over the network multicast. So that's nice. So this is, and if you want to talk about like more detailed things, these get really application specific, but this is a really nice way to kind of distribute some of that load. So, Unix file descriptors have a much lower unbounded latency than network. There's still a buffer. There's still the potential that you may not be able to write to the file descriptor when you want, but it's a lot lower than sending stuff over the network. So summary, don't sweat client-side facing CPU time. It's not a big deal. Move non-client facing stuff away. And then use cluster. If you're using Node right now in production and you're not using cluster, I really strongly recommend taking a look at that. And it's just it's cluster by learn boost, really simple. And that's it. So you can follow me. I'm Shimmer on Twitter with a 1 because I guess I'm kind of old. I've been on the internet a long time. But any questions? I think we have a couple minutes. Yes. Possibly. I think we're working out the roadmap. We're really interested in taking suggestions on what you guys want for Node.js. So please, let us know. We are working on some of that stuff, but right now we haven't published the roadmap. Okay. Yeah.
So you've obviously been using Unix file descriptors. Have you played around with shared memory or message queues for your process?
Yeah, so a bunch of people, I think, use memcached. There's like a bunch of strategies to kind of do that. I think it depends what you want to achieve and what architectures you want to achieve. I think things like memcached are kind of obvious. I think the ability to use file descriptors in Node is maybe less obvious to people. But I agree. Like using something like memcached is a completely viable strategy too. Yeah.
How would you do like sticky user sessions? So you want one user session to always be passed to the same node instance.
Sure. So the question was like, how do you do sticky user sessions? I think it depends what you're building your app in. So whether you do that at like the load balancer, or whether you do that based on something with like Express and actually like set sessions and then use the session handle in Express in order to like redirect.
Yeah, let's assume the latter.
The Express. So I would say you could either use a lightweight Express in front in order to like redirect. So just like an Express app that's just reading the session handle and then passing it off to the right place. So using Express as a proxy, or you could just read the cookie in Node proxy and then use that. Rick?
Do you have any metrics on how much a Node proxy can take in terms of traffic?
I don't. You should ask Charlie. You should ask the Node.js guys. I mean, in terms of kind of, in terms of like Node proxy, I don't know. In terms of a proxy written in Node, I guess it depends on like the profile of your traffic, but we've done tests where reasonable sized servers are doing, you know, very high hundreds of thousands of requests a second without any trouble.
On a single process?
Not on a single process. Like,
so the actual proxy is proxy by a C proxy, not a node proxy?
No, by it's sharded. It's split across. So it's sharing a file descriptor in order to do it. Yeah.
So there's Linux kernel somewhere that is taking 100,000.
It's a Solaris kernel. Because I work for Giant. Cool. Do we have another talk, or is it? I don't know. I don't know if that's the end of it. Any more questions? Okay. Thank you very much. Oh, and I couldn't find a way to put it in the side, but I just think it's really awesome. I mean, it's just, you know, it's a really bad movie that Sean Connery made in like 1974 called I think it's Zazov. Yes, go and watch it because it's terrible. So that's it. Thank you very much.